So let's start a series about why 15 and 290 are cool numbers. And it's going to be a tiny introduction to the study of integer quadratic forms. The basic question that we'll start out with is what positive integers are expressible as sums of squares? And this is also where we started the -163 is cool video, and that's another direction we can go. So there's going to be a little bit of overlap, and it wouldn't hurt if you watch those first, but it won't be necessary. So we've got some number n, and we'd like to know, can it be expressed as the sum of perfect squares? X and y have to be integers here. Let me just tell you the answer in this case, and if you want to know why, you can look at the -163 video. It's a straightforward answer. Okay, either p for primes, if n has to be prime, so suppose this replaced by p, then either it's 2, which is obviously 1 plus 1, or it must have remainder 1 when divided by 4. Another way to say that is p is congruent to, that's the triple equal sign, p is congruent to 1 mod 4. Turns out that that's the answer when it's a prime. Okay, so let's call those primes, the one that are congruent to 1 mod 4, like 5, 13, 17. Let's call those, along with p equals 2, good primes, because they can be represented as the sum of squares. Now, one of the things I actually didn't talk much about in the -163 video was what about the story for composites? I claimed that it was very easy, and here's the answer. You look at the prime factorization, and one simple thing might be, oh, it has to have all good primes in its factorization. That's kind of true. Any good prime can totally be in its factorization as no problem. Bad prime factors are allowed if they're raised to an even power, because then I'll show you an example here that just shows that that's never a problem, no matter whether it's good or bad. So, for example, if n equals 45, that's 9 times 5. Well, 5 is a good prime. It's easily seen to be 1 squared plus 2 squared. And, of course, it's congruent to 1 mod 4. Well, 9 is 3 squared. 3 is not a good prime. It cannot be expressed as x squared plus y squared. But because it's squared, you can just do a little algebra here. This is 3 squared plus 6 squared. You just take the 3 and factor it in. Okay. So as long as the bad primes are raised to an even power, you're good. Okay. Now, in these videos, I'm not particularly interested in the exact answers to when you can or cannot represent these numbers. We'll see what the overriding question is in a little bit. But the main thing I'm interested with this example is that there are numbers that don't get expressed, namely 3 and lots of other numbers. But we don't get a misleading string of yes answers. If we start out with n equals 1, 2, 3, 4, 5, it's not true that we get a bunch of yes answers and get tempted to believe that we could represent every number as a sum of squares. And then when n is 1,000 or a million or a quadrillion or a Google, suddenly you get no. Okay. The first counterexample is very, very quick, and that's going to be very important for us. Now, what about other related questions? We could put in coefficients. We could say, what about numbers that are the sum of a square plus 5 times a square? That's a very famous story that comes into the -163 video. It's a more complicated answer, but it's still true that no, not every number is representable, but the counterexamples start very, very quickly, and we're not misled into thinking, well, maybe every number could be represented this way, and then we discover for n is some huge number, we get the first counterexample. Okay. We could, just to talk about where this could go, we could look at this difference of squares. That was something that I mentioned in the -163 video. It turns out to be, it was where we actually got the first break on how to do this in that context. But I'm actually going to not focus on the differences of squares. So we're not really going to be interested in the ones with the negative coefficient so much. The cancellations that you get make things very, very different there. And in particular, one thing that's true in this case is very different from the other cases, is you can get a large n, a large result, or small result from large x and y. That causes this to be very different. Here, at least, if I want to know if a million can be created out of x squared plus 5 squared, I know I don't have to take x and y bigger than 1,000. Okay. Here, theoretically, I could take x and y as big as I want, and they might cancel down to be a small n. So it's going to be a different story there. Now, it turns out, to be a little more precise, turns out it's not so much the minus sign here. It's the fact that this thing can ever produce a negative number. So what we're going to do is we're going to study only right-hand sides, expressions like this, and I'll make it more precise in terms of generally what we're doing in a little bit. We want to look at right-hand sides that don't produce negative answers, and that they only give 0 in the very special case where all the variables are 0. So here's an example of something that would be legal under these rules. 3x squared minus 2xy plus 3y squared. Okay, so notice I'm allowing cross terms, and we'll talk about that again in a little bit. That can be written as the sum of squares with positive coefficients. It's just kind of not obvious when you first write it out. But if you actually, I claim if you square that out, and add, you will get exactly this expression. Okay, so that actually would be legal, but mainly you want to think, okay, negatives are not really the main thing we're interested in here. So let's go to 3 variables. This is where it goes away from the minus 163 video. We never considered in that thing, in that series, the idea of expressing a number as the sum of 3 squares. Well, that's a very famous story, and let me tell you the answer to that story. Run through at least some obvious or some stuff that's not too hard to see. It gives us a necessary condition, some obvious counterexamples, and then we just have to trust some big theorems from the past that those are the only counterexamples. So here's what we do. It turns out that working with this mod 8, looking at the remainder when you divide by 8, is really neat here. And that should hopefully make some sense, that if x squared plus y squared has to do with mod 4, then x squared plus y squared plus z squared, okay, maybe just go to mod 8 instead of 2 to the 3 instead of 2 to the 2. So here's what happens. Let's just look at what the squares can give you. An individual square can give you mod 8. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared, that's 1. Remember, we're always taking the remainder when you divide by 8. I should have like a congruent symbol here, but I'm not going to worry about it. 4 squared, that's 16. When you divide by 8, that's 0. 5 squared, well, there's a nice trick here. 5 is the same thing mod 8 as minus 3. Well, so the minus sign doesn't matter because we're squaring it. We already have that on the list. 3 squared equals 1. And in fact, 6 and 7 and 8, those are all going to be negatives of something on the list. So we're done as soon as we get to here. So notice what we get. We get 0, 1, and 4, and that's it. That's very limited in terms of what numbers we can get as squares mod 8. So let's just make a list of all the things you could get adding 3 numbers, remembering to always to reduce mod 8 if we need to, and each of the numbers can only be 0, 1, and 4. So I'll leave it to you. It's a good place to pause the video. Convince yourself that yes, you can get 0, you can get 1, blah, blah, blah. You can get 6. Now let's see. Ooh, if 4 plus 4 plus 1, get anything new? No, because that's 8, so that really brings us back to 1. There's not too many possibilities to check, and it turns out you get everything except 7. You never get a 7. So that means that if n is a number congruent to 7 mod 8, like 7, or 15, or 23, there's absolutely no way we can get it. Okay, so that's at least going to be some counterexamples. Let me tell you what all the counterexamples are, because there's actually a simple pattern. There's a nice thing you can do is look at mod 4 as well as mod 8. Remember, any square, just like this thing, it's a simpler version of this argument. It's easy to see that any square is either divisible by 4 or it leaves a remainder of 1 mod 4. So you can't get 2 or 3 when you look at the remainder. Okay. So if I look at the sum of 3 of those guys, suppose I had a number n that was divisible by 4. In other words, it was congruent to 0 mod 4. How could I get that? There's really no other way except 0 plus 0 plus 0. You might look at this and say, let's just think about odd and even. Well, obviously all odd wouldn't end up with a multiple of 4 because it would be odd. And 1 odd and 2 evens, that would be still be odd. But could I have 2 odds and an even? No. If you look carefully mod 4, that's not possible. So here's why that's interesting. If the result is divisible by 4, then all these guys are even. Here's an example to show why that's so interesting. So that shows you can't get 28. So let's do it by contradiction. Suppose you have 28 is equal to the sum of 3 squares. We just made an argument that says that x, y, and z have to be even numbers, so we can divide them by 2. But if you square those guys, x over 2 squared plus y over 2 squared plus z over 2 squared, you're going to get a factor of 1/4, and you're going to get 7. But wait a minute, we know that that's not possible by the mod 8 calculation. Okay, so in fact, you can repeat this argument. Okay, if this was 7 times 4 squared, we could do this argument twice and get a contradiction that we could get down to 7. Okay, so because this trick can be done repeatedly, as long as your number is divisible by 4, here's the numbers that we know we can't get. We can't get anything of the form 8k plus 7. Those are the things that are congruent to 7 mod 8. And we can't get that multiplied by any power of 4. Because if we could get some high power of 4 times 15, say, we could do this trick repeatedly and get down to 15, and we know 15 is impossible. So here's Legendre's result. Legendre proved that you can get everything else, that these are the only counterexamples, and that's way beyond the scope of what I can tell you about in these videos. Okay, but it's actually a very simple pattern, and in a way, it's interesting. It's a little different from the 2 squares case. In the 2 squares case, the way you figured out if a number could be represented is first you look at its prime factorization, and then you do some little modular arithmetic test. Here, it doesn't say do the prime factorization and then do everything. You can just figure it out without the prime factorization at all. Just figure out if it can be written in this form. That's much easier than factoring it. So that's interesting that in the 3 squares case, there's actually an easier answer. It's also a much smaller set of counterexamples. This is a fairly thin set of integers that you can't usually do. You can't actually represent. Now, Legendre, I have to admit, Legendre's proof was flawed, and it's famously fixed by Gauss shortly thereafter. So you can credit it to both of them, but Legendre had the most of the idea. The main thing, this is a good time to stop this video. The main thing I want to get at is that not every number can be represented as the sum of 3 squares, but the smallest counterexample is just 7. So if you were just going to try and test this, you knew nothing about modular arithmetic and Legendre and all these kinds of things. If you just tried to do a brute force test, you would try 1, 2, 3, 4, 5, 6, 7, and you realize, okay, if my goal was to represent every single number as a sum, then it's not going to happen. Okay, so we're going to keep going in the next video on more and more complicated cases of what kinds of expressions like this can represent every single number. Can we find something, and how can we recognize them? And can we test it with small counterexamples and not be misled?